right, I'm recording. All right, today we have Melissa Lucash Working Group presenting as part of our special EDS seminar, celebrating our first cohort of working groups. Woo! Dr. Melissa Lucash is a research assistant professor in the Department of Geography and the Environmental Studies program at the University of Oregon, where her work sits at the intersection of forest ecology, wildfire science, climate change, and spatial modeling. And we're also joined by Dr. James Lamping. He is a scientist in the Parks Postdoctoral Fellow with the National Park Service and the National Park Foundation, based at the University of Oregon. There was lots of talks about floating ducks across screens before you all came in the room. So,
go Ducks.
Go Ducks. He is a forest ecologist and modeler who integrates field ecology, remote sensing, and landscape simulation modeling to understand forest structure, carbon dynamics, and climate vulnerabilities in Pacific Northwest and coastal Alaskan forests. All right, welcome you two.
Thank you.
Thank you, Rachel. Thanks so much for coming to our talk focused on extreme. Let's see, make sure not. So in that upper left-hand corner of our first slide, I had our logo, which if you hadn't noticed, I'm particularly proud of our logo for our working group because, of course, it was designed by my daughter, Celia. She made our logo, and the whole idea behind the logo was really part of the theme of our working group, which was to combine biophysical, sort of the ecological side of extreme wildfire, which is depicted on the right, as well as the human components and consequences of extreme wildfire on humans on the left side of our logo. So when we formed our extreme wildfire working group, we had 5 PIs that were involved in writing the proposal, myself and James at U of O, #GoDucks. And then there was a group they were all at NC State at the time. I have no idea what their mascot is, but it's not important. Rob Scheller, Brandon Sam, who later moved to Carey Institute. And when we started to work on this proposal, we were really inspired by ESIIL's vision and value statement. In particular, that ESIIL was envisioning this world focused on data-driven discovery, and that really spoke to James and I as part of the geography department and spatial data science here at U of O. And then also that it was focused on evidence-based solutions and environmental sustainability, and a lot of Rob and Sam's work focuses on environmental sustainability, as well as Brandon, James, and I. Also, that ESIIL's vision was really focused on this idea that breakthroughs in environmental data science will be precipitated by a collaborative and inclusive research community. And everybody, 4 of the 5 PIs are associated with this ecosystem forest landscape model, Landis 2, that James will talk more about. And our community is extremely collaborative and inclusive. In fact, we just held a training last week of all new users. And this has been part of the Landis community since the early 2000s. And also focused on that open and ethical data was part of the focus of ESIIL, has been open source code since 2015, which doesn't sound like a long time ago, but it was really envisioned and built during the era when we had these very monolithic models that were really large and cumbersome and controlled by one person, and they didn't release their data because then someone might steal their model and publish the results. And Landis instead, even though it was built during that era, was designed from the very beginning to be open data, open source code, and to be collaborative with this distributed model of collaboration from the onset. So this really spoke to us and why we in part wrote this proposal. And then, ESIIL just focuses on things that speak to us, big questions. This is research that all of us do, focused on big questions, big computers, and including new people and ideas. And our workshop focused on EWEs, we call them, and I'm sorry if you wanted to hear a talk about ewes and sheep, but instead we're focused on EWEs. We call them extreme wildfire events, but not ewes. Sorry. And as you all know in the room, extreme wildfire events are increasing, and we know that there's multiple factors that are involved. We know it's about the expansion of urban communities closer to forests and other natural vegetation. So this expansion of the WUI, we know it's due to fire suppression over many decades, as well as climate change. And these extreme wildfire events they exhibit this exceptional wildfire behavior, and these often have severe consequences for both humans and also natural ecosystems, not just forests listed here, but obviously shrubs and chaparral communities. And the challenge is that they have this low probability of occurring. And so we wanted to focus on EWEs because, for multiple reasons described here, but also that the definition is really heavily based on biophysical criteria. And these EWEs also are really hard to capture in these current wildfire models. And these, because they have this low probability and high potential consequences, they have this kind of what we consider kind of a unique risk profile. So in these events, you have this greater likelihood that preparation and institutional practices will be inadequate or ill-suited to the demands of the event. And this can reduce the amount of time that's available to mobilize resources, increase the probability of kind of problematic decision-making, both during and after an event. And really, basically, they're really just challenging. They're outliers at the extreme tail of this kind of like right skewed distribution. And so what we tried to do in our workshop was address these four components. So we tried to build a cohesive interdisciplinary research team. We actually built two with slightly different emphasis on each team to synthesize our current understanding of extreme wildfire behavior, isolate gaps in our understanding, and then develop a roadmap for improving the representation of these extreme events into models that represent these different components that are important for capturing extreme wildfire events. And then the fourth one, to build this Docker package for Landis 2 in hopes that this will allow us to make better forecasts of wildfire and hazard risk and the probability of these extreme wildfire events. And so this is our first workshop participants. And as part of this theme of including new people and new ideas, we wanted to, and being open and inclusive, we wanted to have these multiple components of addressed in terms of inviting people to the workshop. So we wanted to have fire field ecologists like Sean Parks and Matt Hurto and Ali Urza, and we wanted to have forest modelers like myself and James and Zach and Tirtha's in the back there and Shelby in the front, as well as social scientists like Brenda, Amanda, Cole, Jennifer, Elise. So many different types of people. We wanted to attend the workshop to better understand these extreme wildfire events. And we wrote a paper. We took really good notes during the workshop, and we formed that into a paper that has been accepted with minor revisions to fire ecology. I still haven't seen the proof, so it might be a couple more months, but hopefully we'll get there. And in the paper, we literally state that the article really came from this workshop that ESIIL funded. And when we think about extreme wildfire events, we know that we've had multiple examples in the past 5 to 10 years of these extreme wildfire events. And that this issue of extreme wildfire events is not just this abstract concept. This is something that many of us have experienced. The Labor Day 2020 here are those really large orange polygons depicted in the map. I forget whether there's 10 or 11, but the stats are kind of staggering, burning 1.2 million acres, destroyed 5,000 homes, 87 businesses, claimed 9 lives, and required 40,000 people to evacuate over this period. And in terms of what caused these events, it's kind of this confluence of multiple factors, but one of the critical pieces was that the fires were caused by these synoptic east wind events. So coming from the east side where James lives, really dry winds coming from the east to the west. And they weren't, they were averaging 20, 30 miles per hour, but the problem was that there were these huge gusts up to 100 miles per hour, and bringing that dry east wind then intersected with those high fuel loads that we have on the west side, because it's really wet over here. But because you're bringing that, we have these high fuel loads, but it was the beginning of September, so fuel moisture content was really low. It had been dry. Our summers here are really dry, and so we have really low fuel moisture content. We have the east synoptic dry winds, and then you had those topographically complex conditions of the Oregon Cascades, and they kind of came together to create these extreme wildfire events in Oregon, these Labor Day fires. And it's hard to find a good picture to kind of depict what it was like. This, I think, makes it look a lot better than what it really was. It was very dark skies. It got really dark really early in the evening. It was very dark. It had red glowing skies, and at
Looked like the
times,
upside down from.
yeah, it was kind of like Stranger Things upside down. And there's like that scene where the kind of like I don't even know what it is in Stranger Things, where it's like sparkles or something. It was like that almost, but it was like blackened sky and ash falling out of the sky. It felt very apocalyptic. So these extreme wildfire events speak to us both from a research perspective and personal perspective as well. The paper is organized into these different sections, and the talk is kind of organized in the same way about how extreme wildfire events are defined, what are the problems with the definition, how can we revise this definition a little bit, and then what are the gaps, and kind of a roadmap forward for improving extreme wildfire event research in this domain. So I'll kind of start with the first one about how is extreme wildfire currently defined. And one of the issues is in the media, for example, and sometimes even researchers, they often use these terms of megafire and extreme wildfire and disaster kind of interchangeably to label these wildfires that have extraordinary behavior, but they're actually quite distinct concepts. And there'd already been a paper talking about the problems with the definition of megafire, because megafire is specifically defined based on fire size. And in the US, it's considered megafire if it's like just over 4,000 hectares, or it's like 100,000 acres. So if it's larger than that, 100,000 acres, it's considered a megafire. But the problem that was described in this paper is that even though that's the way it's defined in the US, it's not really applicable necessarily in other areas. So it's based on fire size, but there's not a universally accepted size threshold across the world. And what's a large fire in one area is not necessarily a large fire in another area. And, I went to Vienna a couple of years ago, and they were talking about their megafire, and it was like, 4,000 acres or something really small. So much different applications of what megafire is. And there's been all this ambiguity. And so people have stopped using megafire quite as much and now moving to this extreme wildfire event. So it's becoming more popular because it's not defined by size per se, but it's really trying to focus on kind of the complex nature of the events and the relevant biophysical dimensions of the wildfire, focused on these rare, extraordinary events. So there had been a paper published a few years ago by Tatum, focused, and they define EWE with these different components. So you kind of read them, but they're this idea that an EWE is a pyroconvective phenomenon with an overwhelming capacity of control. And they put very specific criteria on what that meant. had to be a specific firelight intensity, a specific rate of spread that it was exceeded before it became an EWE. It exhibits really long distance spawning events and has erratic and unpredictable fire behavior and spread. And then the final part of the definition, that was kind of the biophysical side. And then the social side was very, in our view, kind of vague. So it just says that these EWEs represent a heightened threat to firefighters, communities, infrastructures, and often results in these detrimental socioeconomic and environmental impacts. And again, it's gaining traction over time. And Tatum did this diagram, and this group was trying to kind of encapsulate these EWEs in this diagram with multiple components together. And it was trying to address kind of the biophysical aspects and the human aspects and which factors influence it. It was trying to integrate how it was affected by suppression and intensity, and then also distinguish between disaster and EWE. And we found this just to be a little complicated and wanted to expand upon their diagram and in some ways simplify it. We have two diagrams, and one is a very simple diagram, but we wanted to be able to separate EWEs and disaster, and then one's more complicated to think about how to redefine extreme wildfire. So this is the simple one that actually James and I worked on, and we wanted to make sure that people understood that EWEs were not synonymous with disasters. And so the diagram is meant to kind of start in this bottom left-hand corner in the white section there and say, and depict how they're different. So on the y-axis is fire behavior, and then on the x-axis is the consequences for humans. So again, in this white panel, there are some fires that have typical fire behavior, and they have minimal impact on people and communities. And these are not EWEs, nor are they disasters. So that's the white box. And then if you go up to this top sort of yellowish box in the upper left, you can have fire events that have atypical fire behavior and could have high, impacts ecologically, but low impacts on humans. And those are by definition could be considered extreme wildfire events. And then you can have other events in the upper right where they're, again, atypical fire behavior, but this time now they have significant impacts to humans and communities. These can be both EWEs and disasters. And then the bottom right is this idea that sometimes the fires are typical for a system, so they're not anomalous fire behavior, but if they have significant negative impacts on humans, then they're considered a disaster, but not an EWE. And we were hopeful that this helps separate this difference between EWEs and disasters and how they're defined. So the second part of our paper was trying to outline what are the problems with the current definition of extreme wildfire event. And we have these sort of different themes, and one is about the fact that we believed that the definition of EWE was a little subjective based on your disciplinary perspective, and that context can play a major role in determining whether it has, quote, detrimental socioeconomic and environmental impacts, because it doesn't have kind of a quantitative metric to it. It's just detrimental. And so we thought that was a problem, because one community can define an event as extreme based on the challenge of suppression or loss of life, and then others might focus on economic damages or cultural loss. And that in general, we articulated that these disciplinary perspectives can really shape how EWEs are conceptualized and studied, with this idea that biophysical scientists really focus on fire behavior characteristics like intensity, rate of spread, And so on the sort of natural side, and then the social side, really, when they're studying it, are really prioritizing community vulnerability and governance and recovery. And there's not a lot of cross-fertilization in these studies of EWE. Also, we felt like the scale of impact is also kind of a problem with the current definition of extreme wildfire events. So, for example, a fire whirl might meet the established criteria that meets that extreme fire behavior thresholds, but it could just cause very minimal lasting impact. So you could have just it could meet the criteria, but maybe just for such a short period of time so that it doesn't have a really long lasting impact. And then conversely, you could have this really slow moving, lower intensity fire, but it could really cause significant damage to infrastructure it wasn't well incorporated into the current definition. And then we were also, because the definition really focuses on just the event itself, it doesn't address these kind of compounding cumulative or second order impacts. And so cause really detrimental health hazards due to the presence of these hazardous materials that are burning. And we saw that at Paradise, where you had all these hazardous chemicals that were produced and found in groundwater after these tires burned after this fire. And that these EWEs can trigger flooding, erosion, landslides, and then you can also have these second order impacts from the human side, where humans are responding to these EWEs. They can do emergency salvage logging or restocking, and the natural recovery processes, or could introduce invasive species, lots of compounding cumulative effects that really we felt like should be incorporated into the definition. I'll turn it over to James for a little
I'll
while.
give her a little bit of a break. So kind of going into the contextual nature of some of the discussions we had, the existing definitions, like we've been saying, they use these absolute thresholds and metrics of fire behavior to define these events. And what really constitute extreme conditions in one context, let's say in one region of the United States, other part of the world. So we suggest that we kind of define extreme wildfire events and characterize them by looking at distributions of fire behavior and fire size and things like that, and define them based on these outlier events for a region. Let's see if my control of her slides actually works. Oh, hey, it did. So we like to kind of implementary understands. We propose to find fire events that's a bit more inclusive of things like impact to communities, loss of structures, a community's ability to respond and their capacity. And then suggest that wildfire events or sets of events is labeled as extreme, some theoretical, empirical, or practical meaningful dimensions. Things like just known distributions of fire size, distribution of how fast a fire may spread, forest type. Also understanding things like geospatial and temporal scale when defining these fires, and then understanding, like I was saying, the impact and response capacity of local communities. One of the next figures that we made to kind of build on these, helping define EWEs, is more of a figure that helps kind of a flow of defining a EWE or a disaster is or none of them at all, just to make it a little bit easier to understand like how you go about defining an event like this. So kind of start off at the top with wildfire ignition or fire is detected. And then you get these little hash lines where you think about, all right, now we need to do some kind of comparison to known data. So you compare fire behavior to historical benchmarks, and that goes into asking if fire behavior is out expect to see in a region. So if yes, you go to an atypical fire event with potential for high impacts ecologically. So next thing we got to do is check for community's capacity to control that fire. And if that fire does overwhelm that capacity, you kind of move down into the next bracket and determine whether it's a disaster or not. And so if it does exceed the capacity, an extreme wildfire event, and it's a disaster. If it doesn't, it's an extreme wildfire event, which has its own, implications. Kind of going down the other direction on if it's an atypical fire or if it's a typical fire event, you can go down disaster classification and also look, if that fire does exceed the to deal with a fire of that size. And if it's a yes, it can still be considered a no. It's probably just a typical fire for that region. So it's just is a figure that we added to our publication just to kind of simplify some of the definitions that we were discussing. And it's a bit based on that original figure that we saw in Tadim's original paper.
We spend a lot of time in our working group and a lot of spirited discussions around what are the gaps in our understanding of extreme wildfire events, both during the workshop and in evenings of meals, chatting a lot about what are the gaps and what are the kind of the roadmap forward for filling those gaps. And one of the things that we talked a lot about is that a lot of our fire databases start in the mid-'80s. And that this is already a period where we've seen increases in fire size, so that it becomes really challenging to capture these extreme wildfire events when you have what we consider to be a fairly short period. So for example, in James's diagram that you talked about, are they outside the historic range of variability to assess whether they're extreme or not? That's really challenging when historical only starts in 1984. And there are databases that go back further in time, but they have problems associated with it. Like the Alaska Fire Database goes back to the 20s, but it's just fire perimeter and not fire severity. But just in general, a lot of our best data sources that we have start fairly recent databases. One of the other gaps is that our fuel data is often not spatially complete. It often doesn't have the necessary spatial resolution and the necessary temporal resolution to be really meaningful when you're focused on that scale of active fire spread. And these limitations really hamper efforts to try to model and predict fire line intensity, rate of spread, and other behavioral metrics that are important for EWEs. And one of the other components is that there's limited meteorological data used to model fire behavior. And it's often also not, doesn't go back very far in time, or it's very coarse resolution, created in some of these topographically complex areas. And that these together, improving fire history, improving fuels data and climate data, we thought would really help improve model calibration and enhance the kind of situational awareness during fire events, as well as predicting future fire events. Another substantial gap is really in our limited understanding of how these EWEs impact communities and how social dynamics really shape community vulnerability in their response. And so we thought one of the gaps was really that we could really use more comprehensive, fine-grained social data to better assess whether an extreme wildfire event exceeds a community's ability to cope, and really focused more on developing more spatially and complete fine resolution data on environmental, built environment density and land tenureship, firefighting resources, and demographic vulnerabilities. And we have lots of that data. It's just not in a comprehensive fine grain that is really critical for capturing and understanding extreme wildfire events. The other thing that's often missing is it's really hard to kind of post hoc understand how suppression actions were carried out, both kind of the spatial pattern of them as well as their effectiveness. So if you're trying to model extreme wildfire event and behavior, you have to assess how suppression affected the spread of the fire and the intensity of the fire, and that can be really challenging. Let's see. We thought that there was great potential for lots of this emerging technologies like cell phone reports and GPS data, traffic surveillance, and we thought that could be really helpful for reconstructing social responses like evacuation timing, route choices, congestion patterns. Amanda Stasowitz on our team does a lot of this research. And we thought that integrating this information into predictive models could be improved by accounting for more complex human dynamics about issues with trust in authorities and how that affects evacuation, fire preparedness, community cohesion, reliability, institutional capacity, and really that there's this limited understanding of how these EWEs affect communities and how those social dynamics shape vulnerability and response. Finally, we felt like the interdisciplinary nature of these EWEs really really requires this collaborative, integrative approach, and that shouldn't just focus on the biophysical science, that it should span these multiple disciplines like data analytics and social science and community-based practice research, and that it should engage a wide range of stakeholders like emergency responders, as well as Indigenous partners and researchers. We thought that that would improve both the relevance and effectiveness of research, and that we should also focus on public engagement and co-production of knowledge, and not just focusing on this very narrow biophysical emphasis. Ultimately, we felt like it was important to establish metrics to evaluate the effectiveness of public engagement initiatives, focusing on shifts in knowledge, behavior, community resilience, and really trying to translate scientific findings into accessible formats and involving citizens in both data collection and planning, and that hopefully that would enhance buy-in and strengthen local capacity. Finally, we talked a lot in our group, because we had a group of wildfire modelers, about the fact that a lot of these climate models and climate data that we use really focus at produce output at coarse spatial and temporal resolution that really limits the ability of modelers to capture these really localized and short-term meteorological phenomena, like in the east wind events and the Labor Day fires, or heat dome events or drought events. And that a lot of the climatic conditions that cause extreme wildfire events are these statistical outliers themselves, the climatic events are, and then they often get smoothed out or really underrepresented when you do these ensemble climate projections where you're using a median or mean from multiple SSPs from a particular GCM. And that a lot of time these climate models are aggregating the data either to daily or monthly time steps, and that can be a significant challenge for calculating fire weather index that's used in a lot of these models. And ultimately what happens in terms of wildfire modeling is that we often fall short in representing that complex, nonlinear, and interdisciplinary nature of extreme wildfire events. And that one of the gaps is that ember transport, for example, is captured well in physics-based models, but they're only applied in really small scales. And then these ecosystem and learned surface models where you have them operating in a landscape or global scale, they don't adequately represent, for example, ember transport. And ember transport is really a critical process, and it's really unique in that it can lead to these spot fires in what we consider as kind of safe areas. And these are these ember transports are often underestimated or not included in conventional fire behavior models, and that can pose serious challenges for really predicting fire spread into these urban areas. Also, we felt like one of the future directions of fire modeling and extreme wildfire research should really focus on this coupling fire behavior with this understanding of the social fabric of communities and their physical layout. So like vegetation, roads, buffers, and really try to integrate perspectives from multiple disciplines to ensure that the results are usable by local governments and aligned with community needs. And we had lots of ideas about this roadmap and future research with improved fire modeling, about better documenting and mapping building design, landscaping, building materials, trying to extend model projections beyond just modeling fire behavior, but also looking at long-term impacts like post-fire erosion and changes in. Back to James.
So what Melissa just went through was the findings and discussions we had in workshop 1. And like we said, we brought a bunch of interdisciplinary scientists together to have those discussions. And in workshop 2, we actually used that workshop to be a bit more targeted, taking what we learned and discussed in workshop 1 and then directly trying to implement some of those things into the Landis 2 modeling environment. So what you see here is workshop 2. It's a bit smaller of a group, but that group is all pretty much Landis, have all used or have been involved in developing Landis extensions in the past. So you have folks like who actually designed Landis 2 and there. I'm in there in the middle. We have Shefford, who Landis for a number of years, Matt Hurteau, Brian Sturdivant, Zach Robbins, who made one of the fire models in Landis. At the Clearwater, Adam and Sam Flake. And the only one who hasn't actually worked in Landis too often is Adam, but he works in a more physical dimension of fire modeling that we hope to integrate into Landis. So it was a pretty targeted group. And can I advance the slide? Can. And we really wanted to discuss how to improve Landis 2 and how it represents wildfire based on all the discussions we had in the past. So you can kind of see some photos here of us around in a circle and brainstorming. And it's really rare that this group of Landis modelers gets to do something like this. We're all over the place. You know, we live all over the country, all over the, and being able to get together into one room and have these discussions and hash out future plans for Landis modeling was really helpful for us. Melissa, go back. There we go.
That's the problem with co-host.
So, challenges we kind of talked about in this extreme model, our climate data can be normalized and we start missing, or extreme weather events start to coincide to make an extreme wildfire event more likely. Representation in our models of things like fuel moisture or ember transport. How do we get about trying to add those to our models? To other models, right? So Landis has its ability to model, but it also has an inability to look at finer scale things. And how do we link our model with other models to kind of that gap of scale mismatch? And then the big one that we always have is computing resources. The larger and more complex our models become, the more compute power we need, and we start getting pretty close or pretty quickly beyond our ability to run Landis models at a local desktop. One of the deliverables for this workshop was trying to come up with a guideline on proposals we want to put in the future to push Landis into modeling and addressing those gaps we identified, and we were able to do that. It was a really great success and it was a lot of fun. But I'm going to kind of talk about how ESIIL and Cybers helped us with that last problem you see highlighted, their computing problems. So a big part in the background of these two workshops was integrating Landis 2 into the cyber computing environment. And that started kind of a long time ago before we had these work with, that started a long time ago. And we'll explain what Landis 2 is because we've been saying it a lot, but we haven't really described what the model is. So Landis 2, open source, it's a spatially interactive, spatially explicit model, which means that you feed in maps, so spatial maps, and it outputs spatial outputs, things that happen in the environment that would let trees grow and die. And it forecasts interactive effects of things like climate, succession, different management regimes, multiple disturbance regimes. It's used all across the world. It's very popular. Oh no, man, this is actually, there we go. It's used all across the world. It's a very popular model, and it's really dynamic, right? So the model to kind of work in any environment based, disturbance regime, management regime you want. It's pretty plug and play in a way that you can manipulate, or you can choose different extensions within the Landis model framework that model a certain specific event based on the questions you have for the four. So here of a lot of the different extensions that we have in Landis. They've been developed by different people all throughout the world, and they're all hosted open source. So, we have, like you see at the top, these succession extensions, and they control things like tree growth and tracking things like new. And then these other extensions do a variety of different things, like they have wind extensions for modeling fire in different ways. We have different output extensions that output different types of maps, things like EDA, biological disturbance agents, so things like bugs. So that, you can choose any mix and match of any of these in your models and kind of run your models based on the questions you have, like I was saying. So it's a pretty dynamic model. And the goals that we had was to add scalability to Landis by integrating Landis into Cyberse, allow access to more computing resources because the larger your landscape becomes, the more memory you use on your computer, and you need to start moving into things like high-performance computing environments. And then we wanted to improve the of Landis. Whenever you download an extension in Landis, it's a .exe file, so it gets loaded on your computer, and it's a little difficult just to track what version someone used over time and publish that data. So we wanted to improve the reproducibility of someone's Landis model runs. So like I was saying, the original stab at this was before we did these ESIIL workshops. Shelby Weiss's PhD work. She worked with Tyson Swetno operating what I think was Cyverse's Atmosphere environment. So running a Docker package on Atmosphere. And then over time, we've continued work in the Landis community, building out, a bit more complex and complete containerized versions of Landis for Linux. A lot of that work was done by the Canadian Landis 2 developers, Alex and Clement. And I help here and there in trying to maintain these repos. And here's kind of what it's evolved into. So on GitHub, you see kind of all these different flavors of Docker Landis based on whatever model version you're using. Back when this all started, we were using 7, but since then we've upgraded to V8. So you can see both of those are hosted there for people who want to run V7. They can run it in. And then there's some other flavors for that contain things like R and RStudio. So you can do some geospatial processing on the tail end of running your models. And each one of these contain just 2 components. One of them is the Docker. So on the left, you see the container. And that's static, so that never changes and builds the Landis landscape or the Landis model environment that can be hosted on a high performance. Pretty much it can be hosted on anything that runs Linux. And then on the right side, you see a YAML. So that YAML is designed so that you can actually point it to any version of any extension that you want to build in Landis. And this is the one file that can change. This has whatever Landis extension you want, and then whatever commit version on GitHub that you want to build off of. And so the idea is that you edit this YAML file, and then you can build any version of Landis that you'd like. Your data and your results, you can also publish these two documents. And the reproducibility of Landis becomes a lot simpler. Anyone can run whatever environment of Landis that you built and ran your models through going forward. So with this structure, we've been working with one at ESIIL to try to get this implemented into the Cyberse like application environment. So right now we're working a lot with Ashish to build out an application that can be scaled out to any Landis user who has access to Cyberse, and they just submit their YAML file, their version of Landis on the disk in Cyberse. Eric helped us a lot in the first workshop, and Ashish is helping us a whole heck of a lot in the second workshop. So he's been there the whole time. So we just really appreciate all the help we've received from you all at ESIIL. So kind of to summarize everything, given the current climate trajectory will become a lot more common and will really influence the future of our ecosystems and human communities. Addressing the research needs outlined in our two workshops is really paramount in improving our prediction capability and our management of these extreme wildfire events, and then giving the growing uncertainty about system feedbacks, kind of these nonlinear thresholds that we see in these extreme wildfire events. Whatever climate futures come our way, researchers really need the data. We need the tools to engage with communities to help us prepare for these high risk, very low probability fire events. I think there's one, I can get it to go. Yeah, thank you. There's your duck. Yeah, you get the duck now.
So what questions do you all have for Melissa and James? And if you're on Zoom, feel free to unmute or add your question to the chat and we'll get to it.
I have a few questions, but I'll start with my favorite one. Incorporating the social aspect of this immediately made me think of like Bend, Oregon versus Arlington, Virginia. And so Bend, Oregon has 200 years of cultural integration of fire, and they have resources and they know how to do it, and there's just a culture behind it. And Arlington, Virginia is now seeing fires, but they don't have this culture. So in terms of modeling and in terms of incorporating those social dimensions, how would we sort of go about comparing those two places?
You want to talk, James? You want me to?
I mean, just, a lot of the issues we have on this input side is just knowing, let's say culturally, what those two communities, for Bend, Oregon, I know there's a lot of, prescribed burning and thinning in this. I mean, I live in Deschutes County. We're really good at trying to manage fire within our communities and then restore events. And then for communities that just don't have a history of either responding or managing for wildfire events that kind of encroach. One ability that we have with, let's say, modeling is saying, okay, well, this community does this practice here in this way, right? So we do thinning, we do prescribed fires. So what happens if we implement that same practice in this model for an East Coast community? What are the effects and what are the intrusions into the lived space? Can we try to project out, what their fire risk in those communities might if we had the same management style? And will it even work for that environment? Like, does that kind of management style even work for an East Coast community that has hardwoods? I don't know. That's kind of like the predictive power we bring, but there's also, right, we're going to integrate finer scale processes like physical fire models. Exist and what are they made out of?
They're specific, like the Western wildfire, I forget what it's called, like Western Wildfire Research Collaborative, I think, to bring together Western and Eastern wildfire researchers together to try to kind of bridge across these divide of sort of like people that have long been focused on understanding and making projections about wildfire, and then people who haven't sort of needed or been focused much on wildfire, and bringing those communities together to kind of inform each other.
Awesome. Thank you.
I'm going to ask a question. No one else has a question. We probably have time for one more, and I hate to take it, but I will. What advice do you have for other ESIIL working groups, or those thinking maybe of applying for an ESIIL working group? What advice would you give them?
I think that it was really helpful to, like, just the way you do your planning, just to be careful in what you propose to do, and that ESIIL can provide, that you develop goals that are achievable given the people and resources that you have. And so that's one. And then the other one is just, I felt like the best part of this whole experience was just getting to spend time, number one, with the first workshop with a group of people from all different disciplines and perspectives. And I thought that was really fun and helpful. And so I encourage new groups to have both time to sit in a room and workshop ideas, but also go out to dinner and chat about ideas and think about next steps. And I thought that was one of the best parts of our workshop and the most fun. James?
Yeah, I mean, I think one of the greatest things about the working groups is, like ESIIL itself, and your guys' partnership with Cybers is really data focused. And our groups are mostly spatial data focused too, but getting us all together, like the whole community of wildfire modelers or people who think about wildfire, just getting together in one place as cool as Boulder allowed us to just, talk and just all really want to see from each other. Like, it wasn't like, I'm a modeler and I want to do this. It was like, hey, I'm a social scientist and I need this from, like, well, we're modelers and we need this from you guys. Like, it just had together was really helpful. And then creating like social spaces outside of the working group like time frame. So not just meeting on campus at a restaurant and having lunch or going out to dinner together. Like every night we kind of had a scheduled dinner where we all got together and had more conversations. So I thought it was a really great environment to get like actual people together to have actual conversations and then leave with actual products or like, and then on the spatial side for us that we're doing like behind the scenes with Ty and other folks at ESIIL and Tyson. But you were all super helpful, and now we have Landis working up in Linux, and I would say if your goal is to get some kind of spatial an ESIIL project, always super helpful and willing to work kind of outside of the workshop to get something up and running before workshop starts. So reach out and make sure that you say, hey, I need this to work on the Cybers computing environment before the workshop, and you guys will help us get it done. It's like impressive how fast you guys help.
Awesome. Thank you.